Namaste. I am Amrutha pursuing my bachelor's in Metallurgical and Materials Engineering, 7th semester at Mahatma Gandhi Institute of Technology, Hyderabad. My partner for today's talk is P. Janaki Ram doing his bachelor's in MME at MGIT, Hyderabad. I had done a review on narrow gap laser welding of structural steels in my third year under the guidance of Dr. Rahman Rashid from Swinburne University, Australia. We are glad to have obtained an opportunity to deliver a small talk on this huge virtual platform of eBTTD. Today, we would be focusing on the following content. Starting off, there are many reasons attributing to the advancements in joining processes. The very first is the increasing demand in the mankind, and secondly, it is the increasing demands in the strategic sectors, that is the aerospace, nuclear, and defense sectors. These sectors need advancements to increase their service and to maintain longevity of the structures. Additionally, the conflicting demands of the mankind so as to have both comfort, safety, and emission reduction and sustainability have been the prime motivation to choose this topic for our research. Advanced high-strength steels have come to the rescue due to their metallurgical stability, high corrosion resistance, good creep, and ductility properties at elevated temperatures. Typical challenges that are faced during the welding of AHSS steels are the induced tensile residual stresses caused by the high coefficient of thermal expansion of steels, the lack of fusion between welding tracks and groove side walls, hot cracking porosity and resulting in the degradation of mechanical properties, and reduced corrosion resistance of the welded components. To overcome these challenges, high welding speeds with high heat density and narrow gap width joint configuration must be implemented. Narrow gap laser welding promises to be a flexible process because here the laser beam is transmitted through an optical fiber to the inaccessible areas for fabrication of thick section steels. This multi-pass welding process contains an added filler whose function is to enhance the quality of the weld and also effectively tailor the microstructure and mechanical properties. A trailing shield gas like helium, argon, or nitrogen is also administered during the process to avoid atmospheric contamination. Some key advantages of NGLW over the other joining techniques are that it allows high welding speeds owing to its high power density, thereby resulting in increased productivity. Consequently, the distortion and residual stresses are lower due to low heat input. Moreover, this technique produces heat affected zone that is narrow due to the narrow bead width. Besides steels, NGLW has proved promising for welding aluminum alloys, nickel superalloys, and titanium steel bimetallic sheets. NGLW comprises of 4 basic steps. First is the designing of the groove, second is the machining, third is autogenous root weld, and lastly it is the welding of the remaining depth with laser and filler. The following fishbone diagram depicts the input parameters that govern the weld. It is important to maintain near identical chemical composition of the filler to avoid difficulties during welding. Speaking of laser, a high power laser produces metal vapor, hence the power must be optimized. Also, using defocused laser beam, which provides larger defocusing distance, thereby leading to direct energy transfer, which in turn melts the sidewall. The main characteristic of the shielding gas is to effectively isolate the weld zone from the atmospheric contamination. Moreover, the consumption of shielding gas is reduced significantly when it is directed inside the groove. To obtain smooth weld seam, it is also important that the droplet transfer is in the surface tension mode. Hence, by following and optimizing these parameters, the weld will contain the following output, which would definitely have superior mechanical properties, excellent bond strength, defect-free weld, high efficiency, and a tailored microstructure, and also the process economy. Now, I request Mr. Janaki Ram to take over the presentation.
Yeah, if I talk about microstructural characteristics of NGLW joints, this processing technique is almost related to laser cladding process. The product obtained from NGLW process is subjected to high cooling rates of almost around 400 degrees Celsius per second. So therefore, the microstructures in the root weld and the filling weldment greatly vary. Use of high laser power or low shielding gas during root welding can result in concave meniscus at the bottom. It is because of the upward capillary action of the weld metal, as you can see in the figure. And interestingly, shape of the surface of the weld after each pass can determine the lack of fusion. One report says that lack of fusion takes place in the convex and flat surfaces of the weld joints, while the concave surface of the weld joints represented the complete fusion. The morphology of an NGLW joint is characterized by head-shaped fusion zone. The fusion zone in the steels mostly consists of martensite phase in both tempered and untempered states, along with the presence of other phases such as ferrite, retened austenates, and carbides also. It all depends on the filler material and parent material combination, and also on the thermal cycles experienced during welding. The NGLW technique exhibits a special directionality in the columnar region of the weld bead with an equiaxial region in the center. They also found that the degree of the hardness was highest in the capping pass, which you can see in the figure, and that hardness is again decreasing after post-weld heat treatment. You can observe an uneven hardness in the weld joints, right? Which another study reported that there is a presence of cellular grain morphology which resulted in this uneven hardness distribution. Coming to the mechanical testing aspects, during the tensile test of S960 steels, it was found that the failure occurred in the base material which was away from the welded region with optimized parameters. Reports also stated that when unoptimized parameters were employed, the UTS in 316L steel dropped drastically to about 512 MPa. In other steel D406A, NGLW process proved superior to GTAW as homogeneous tempered martensite was obtained in the microstructure. The other part of the presentation is NGLW process defects. One of the major issue with this is lack of fusion, which occurs between side walls of the groove and weldment. And the other one is weld root cracks, which arise due to incorrect selection of process parameters. To obtain a defect-free weld, the width of the lower selection of the weld bit should be lower than the groove width, or else incomplete interlayer fusion takes place. And in some cases, when the liquid metal solidifies much faster than the required rate, then entrapped gases and slag impurities do not get time to escape. This causes unwanted porosities and inclusions. The remedies for these defects is to use low medium laser power and low wire feed rates, and alternately it is also suggested to increase the defocused distance of the laser beam. By using oscillating laser beam, you can avoid solidification cracks, and porosity and inclusions can be avoided by laser cleaning process. Moving on to the conclusion, industrial demands for improving quality and productivity resulted in development of advanced welding technologies. Although there are many welding technologies, but there are restricted up to 50 mm thick structures. For this, NGLW has been found to be a good solution for such application, and productivity also increased very much. Research towards welding in 2G and 3G positions has to be carried out, and the effect of corrosion resistance on the welded components must be studied. This brings us to the end of the presentation, and these are the references which we have taken. Thank you for the patient listening. Thank you.